All right. We'll do this last little section. Like I said, we'll be done. Okay. So this first one, constellation. So historically, and the Greeks were really good at this, or at least they did a lot of it. Um, when looking at the stars, they kind of assign shapes and patterns to them, and then related that to uh, their own mythology and religion. Uh, a lot of these, I think, takes a pretty good imagination to see what they saw, but uh, yeah, they must have a better imagination than I do. Um, this constellation is shown in this picture is Orion. Um, so Orion's belt is usually pretty easy to spot in the sky because it has those three stars right in a row like that that are pretty close together. Uh, also, so they where a star's color is included as temperature. It shouldn't be surprising since we've had other instances where color is indicative of a temperature. So it shouldn't be too much of a surprise that stars are the same way. They're yellow, orange, red, blue. Those temperatures determine the color. Okay, next one. Binary stars. So this is where two stars are close enough to where their gravitational forces influence one another. If these two stars are the exact same mass, they're the same size, mass, not necessarily size, but when they're orbiting, they'll orbit one central point and it'll be smooth. Um, at one point, right in the middle, it'll be very uniform. But if one's larger than the other, then it kind of starts to do kind of a strange thing where it's kind of a wobble. Astronomers can look at that. If they see that, then they know that one star has a larger or greater mass than the other. And it's binary stars. They aren't uncommon. The sun is not one, but they are a fairly common thing. Let's see. All right, this one I would kind of take note of, and maybe kind of put in the mental database, because this is something that's kind of a misconception and misused quite a bit. Is it a light year? Is a measure of distance. It's not a measure of time. Typically, if you're talking about years, you're talking about time. How long has it been since you saw so and so? I don't know, 2, 3 years. Typically it's a expression of time. A light year, though, is an expression of distance. It's the distance that light travels in 1 year, which is about 5.8 trillion miles. It's a long way because light's really fast. Over 670 million miles per hour, around the Earth 7.5 times in a second. Yeah, I mean, it's fast. But like I said, I would remember that a light year is a measure of distance, not time. Even though it sounds like time, it's distance. The Hertzsprung-Russell diagram. I'm not going to ask you to memorize anything on this. I would just make sure that you can pull some information from it. And it's really not a lot of difference from just pulling information from a normal graph. You have temperature at the bottom on the x-axis. The only thing that's a little different about this is you have the higher temperatures on the left and kind of the lower temperatures over here. So typically that's flipped, but that's how it's set up on this one. Here you have the absolute magnitude. So this is let's do the size and brightness. You have the sun kind of in the middle. So it's pretty much, right in the middle of the absolute magnitude. It's a little on the cool side as far as the temperatures go. Um, but I mean, it works out well for us. If it were any, warmer, it would probably be too warm for us here on Earth. If it was any cooler, same thing, it'd just be too cold. But again, the big thing with this, I'd just be able to pull some information from it if asked to do so. Oh, right, a nova. So when a star explodes, gets really bright for a short period of time. If it's a really big star, then it undergoes what's called a supernova. Same process, it's just bigger. Some of these throughout recorded history, there have been writings about things that, like this, that, people were aware of, but they didn't necessarily know what they were because, they were, hundreds of years ago. But, since then, reading through, historical accounts, scientists can figure out that this is, probably what this was. Some of these were so bright that they were actually visible during the day, which, I mean, that would require something to be pretty bright to be visible during the day to kind of, compete with the sun like that. Nebula, we've seen this a few times. This large cloud of gas and dust. Again, when I say large, I'm talking solar system size or larger. These things are massive. The nebula on the left is called the Horsehead Nebula because it has that little kind of shape in there that looks like a horse head. One of the fun facts for the day. All right, so kind of the life cycle of a star, even though a star is not alive, so to speak. Just like anything that uses fuel of some sort, it's going to run out eventually. And large stars tend to do that more quickly than smaller stars. The larger they are, the more fuel they're using, so they burn through it faster, versus a smaller star, which doesn't burn through as quickly and lives a lot longer. So here's a supernova that I had mentioned, and kind of the cutoff for the size of stars that will go through a supernova versus a nova is about 3 times the size of our sun. So our sun will go through a nova. The stars that are at least 3 times as large as our sun will go through a supernova. Only those larger stars even have the potential to create a black hole. Our sun will never produce a black hole because it's not big enough. It doesn't have enough mass that when all of that kind of collapses in on itself, that it's going to form a black hole. But if it was 3 times or larger, at least, then that could be a possibility. And this graph or this diagram kind of shows the life cycle of a star. They all start, the same. The nebula and kind of a protostar. It's just the size of the nebula that determines the size of the star. And the main sequence star portion is just kind of when it's just doing what a star normally does. Burning through fuel, producing energy, that sort of thing. Then the stellar stage. So if it's a real small star, nothing super extraordinary, no huge explosions or anything. It just kind of collapses in on itself. Form a white dwarf or a black dwarf. Mid-range stars like our sun forms a red giant, so it's going to get bigger, and then it's going to collapse into a nebula or explode into a nebula, then potentially go to a white dwarf or black dwarf, and then 3 times or larger red supergiant, then a supernova, then it has the potential to be a black hole, or neutron star, which is just a really dense body that emits a bunch of radiation and stuff. So these are just kind of the generic life cycle. In the universe, there are galaxies. So ours is called the Milky Way, has, you know, billions of stars, planets, you know, dust, gas, all that. Our Milky Way galaxy is a spiral galaxy. It's, you know, pretty good size, 100,000 light years wide, 10,000 light years thick. Milky Way is pretty easy to find. You usually look next to the Snickers, sometimes the Twix, sometimes, or not. Fun fact, if you've ever seen a picture of the Milky Way, kind of like one of these, where it shows where the sun is and all that, it's not really the Milky Way. It's either a picture of another spiral galaxy that looks like the Milky Way, or something that's been created, you know, digitally, or, you know, drawn or something like that. You know, just within the last 5-6 years, maybe, we had something that we created exit the solar system. So a satellite that we produced left the solar system. You know, it's traveled that far to leave the solar system. So we haven't had anything that has traveled far enough, you know, if this is the Milky Way, to get far enough away from the Milky Way to then turn around, take a picture of it, and then send it back to us. And then, you know, we can say, oh, well, that's our galaxy. It just hasn't happened. So, and I hope I'm not disillusioning anybody or bursting anyone's bubble or anything like that. But maybe that's a fun fact for the day as well. That, you know, pictures of the Milky Way, they aren't the Milky Way. Galaxies are organized and classified by their shape. So the three main are spiral, elliptical, and irregular. And then even within those, there are, you know, subcategories and you know, classifications that are much more specific. Like these first two, these are both spiral galaxies, but they're obviously very different. They have different numbers of arms and all that stuff. So, and they can get pretty specific, but, you know, for us, spiral, elliptical, and irregular is fine. And then the last thing, Big Bang, has nothing to do with physicists at Caltech or roommates or anything like that, but it's probably the most widely accepted scientific explanation for the beginning of the universe. And essentially, it kind of states that everything in the universe originated at a central point, and you know, in an instant, everything, you know, has been moving away from that point ever since. Scientists think the universe is about 13 point, I think, 8 billion years old. It's 13 point something. And like I said, everything's been moving out in all directions from that central point. So yeah, and that's kind of the nickel tour of the Big Bang.